So welcome to the second part of the Erlang Express course, and this part is called Sequential Erlang. And what we're going to do, building on what we talked about last time, which was the basic data types in Erlang, together with how you build lists and tuples, which are the powerful data types used to represent complex data, building functions and modules on top of those. So what we'll do this time is talk more about how you write more complicated functions, so talking about conditionals, looping constructs and so on, saying a bit about what's in the libraries, what the built-in functions are, and talking a bit about how errors are handled, so exception handling, the sort of errors that can arise in evaluation of Erlang programs and the way that those can be handled. Okay, so let's move and just have an overview. As I say, what we're going to do in the first part of this is cover conditional expressions, how you branch in evaluation, and in particular talk about recursion, because that's the major way that control it flows through Erlang programs. So we'll start by looking at case expressions. Now what you see in a case expression is it's delimited by the keywords case, of, and end. You have a single expression that is evaluated, and then according to the value that has, you have a number of alternative cases. And in each of the cases, the clauses, you see a clause head and a clause body. The head, you have a pattern, and in the body you have a sequence of expressions. Just like, it's very similar to the definition of a function, where in the head of the function you have patterns for the arguments and a body. Here you have a single pattern which will match against the value of the expression evaluates to, and then a sequence of expressions that are evaluated in that particular case. The patterns can involve unbound variables or bound variables. In the case that they're unbound, they get bound just in the way we saw with function evaluation. The case here is a very simple one. What you've got are true and false, the atoms true and false, which represent the Boolean type. And in the true case, you return OK. In the false case, you return the tuple, beginning with error and ending with unknown. Clauses are separated just like function clauses with a semicolon, but there isn't a separator after the last clause because they're separators rather than terminators. Okay, the general case looks very much like this. You have a number of patterns. It says in the slide, one branch must always succeed. The point is, if no branch does succeed, what will happen is an expression will be raised. And we'll see an example of that later on in the third part of this sequential Erlang chapter. It's possible to make sure that a branch always succeeds by putting a wildcard or an unbound variable in the last clause, because that will always match, even if all the previous clauses have failed. Evaluation is just as it was for function definitions, that is, you check the value of the expression against the first pattern. If that succeeds, you evaluate the expressions in the corresponding body. If it fails, you go on to match against pattern 2, and so on. As you can see, if you reach the end and it's a wildcard or a variable, you'll definitely match that. But if you don't, as I said at the start, if you don't match, then what will happen is that you'll raise an exception. Okay, so that gives an overview of a case statement. What I wanted to talk about now is just an approach to programming that Erlang encourages, or the Erlang style encourages. What we've got here is a function that takes a day, passed in as a variable day, and days are represented by the atoms Monday, Tuesday, Wednesday, and so on. And what this is doing is converting that day into a numerical code for the day. So Monday gets converted to 1, Tuesday gets converted to 2, and so on. And what we've included there is the final catch-all clause. And what that says is, for any other input, what you return is a tuple beginning with error, so signaling there's an error value there, and just returning the atom unknown day in the second half. So what this says is you program defensively, you've programmed in case of any possible input. What this means is that the result of this function, now it could be an integer from 1 to 7, or it could be a tuple. So there is a problem now that you've programmed defensively, so now anybody who uses this function potentially has to deal with the case that there is this error tuple gets returned. And the Erlang style tends to be not to program defensively, but to let it fail. If you've passed in something that isn't a day, then it's your problem. You ought to recover from that. So the Erlang style is to let it fail, so remove that red text, and simply have a case statement that doesn't match every possible input. It only matches the inputs you want to, and in the case where you pass in something, I don't know, a month or a year or a number or whatever, an exception will be raised, and it will be up to the caller to handle that exception. So that's the Erlang style. Let it fail. Don't program defensively. Okay. The other form of conditional evaluation is the if. And if again is delimited by the keywords if and end. There are a number of if clauses which again are separated by semicolons. What comes before, what comes at the head of each clause is a Boolean expression called a guard. Now this is, if you're familiar with other programming languages, this is a place where Erlang differs from other languages, that guards are not arbitrary Boolean expressions. And so the next few slides will talk through exactly what guards can be. But you can't write, for instance, a function call inside a guard. The idea is that guards should be evaluated quickly, guards shouldn't fail, guards shouldn't go into an infinite loop, guards shouldn't have side effects. And so there are syntactic restrictions on what you can put into a guard expression. Guards can appear here. In fact, they can also appear in other places, which again we'll talk about presently. The general form of if is we have a number of clauses. The the guard expressions are evaluated in turn from the beginning, and the first guard which evaluates to true has the expressions in the corresponding body evaluated. So if the first guard is true, you do the first set of expressions. The second guard is the first is false, but the second is true. You do the second, and so on. If you want to make sure that every case is handled, then the final case should be the value true, the atom true, and that will be the case. That will be the else case, effectively, that you will handle in case all the other guards have failed to be evaluated true. It's not mandatory, but if you fail to match any of the guard expressions, you will get an exception, and that will have to be handled. So what I'd like to talk about now is the particular form that guards have. But before I do that, just to mention, as I said earlier on, guards aren't just usable in if expressions. And here you see the first example of using a guard inside a function definition. So what you can see in the lower half of the code sample is the definition of factorial we wrote in the basic Erlang chapter. What we see there is using pattern matching, we can distinguish between the case where an input is 0 and every other case, which might include a number or any Erlang input at all. What we see in the top clause now is after the when keyword introduces a guard in the head of the function clause. So that says this will match any input n, but only if that input n is greater than 0. So implicitly that says n will have to be a number and n will be greater than 0. Now we can say explicitly that n has to be a number, and we'll come back to that in a second. But for the moment you can see that this clause will only apply now when n is a number greater than 0. And then the second clause will apply when the number is 0 itself. So as it says in the remarks, if you have fully guarded clauses, it's possible to reorder them. So the order of those two clauses is independent. We can choose the ordering there. Of course, if you reorder the bottom two clauses, you'll never hit the factorial 0 case, you'll never hit the base case. So now you can see you can use a guard in a function head. You can actually use a guard in a case clause, so mixing up pattern matching there with a Boolean expression, and also in if statements. And finally in receive, which is used in the concurrent part of Erlang. But guards can't be arbitrary Boolean expressions, as I said earlier on. So what we want to do now is talk through precisely what you can use inside a guard. So here's an example of a convert function which takes a string and converts a string or an atom and converts those things into atoms. And what the first clause does is it says when the input is a list, it invokes the list to atom primitive to turn that list into an atom. And of course, when it's applied to an atom, you simply return the argument as the result. So one source of functions that you can use in guards are the is underscore followed by type name. So you can check, for example, is the input a number? Is it an integer? Is it a float? Is it an atom, a PID, a tuple, a list, and so on? So all those checks can be done. So for example, if we go back to the factorial example, we might want to say factorial of x when is integer x x greater than 0 returns the result x times and so on. So there we have a check that first of all the value is an integer, and then we check that it's 0. I'll come on to comma in a second, but in fact it's conjunction, so you're saying it is an integer and x is greater than 0. So what we have also are some built-in functions, like we can look for the length of a list, we look for the size of a tuple, and so on. And we've also got the comparison operators. And here again is a place where Erlang differs from a number of other languages, just in the way that you write the comparison operators. So what we have are, to check equality, you have equals equals. To check not equality, inequality, you have equals slash equals. To check exact equality, you have equals colon equals. An example of the difference between equality and exact equality, 1 and 1.0 are equal, but they're not exactly equal. And the relational operators, to compare whether one number is smaller or equal to another, you say equals less than. To check whether a number is greater than or equal to, you say greater than equals. You have to get those in the right order, and they're not the same operators as you see in other languages. So just beware there. So you have these primitives, you can check types, check length, sizes of composite data structures, you can check ordering examples. So what we'll do now is look at how to put guards together to build up more complex guards. One thing to be aware of is that variables in guards have to be bound. It's not possible that you don't do any variable binding inside a guard. But to compose guards, we can use comma and semicolon. So comma is conjunction, so it says that both guards, it's and, both guards must hold. Semicolon is disjunction, so you can say, if you look at the second example, that is checking whether the input is a tuple or is an atom. And you can combine commas and semicolons. I would advise you to use parentheses if you're going to do that. Now, there are a number of other conditions on guards. Guards must be free of side effects. There's only a restricted set of BIFs, built-in functions, and expressions that can be used. If you want more details, look in the reference manual or in the Erlang programming book. So I guess we're familiar in other languages with being able to put arbitrary expressions inside an if. So how can you achieve that in Erlang? So here's the way that we can deal with the general case where you want to switch on the value of a user-defined function. What we would like to write in Erlang, but we can't, is the code at the start of the slide. So that says if f applied to args is true, the result is okay. Otherwise, so that's the true case, we return an error. We can't do that because it's a user-defined function, but what we can do instead is do a case switch on the result of that expression. So the second example, the second code, is the way we do it. You apply f to args and then match on the result. If the result is true, we return OK. If it's false, we return error. So you can see there's an easy way to transform what we'd like to write into what we can. So that so the general case switch will always be possible. So the second part of the sequential Erlang part 1 is to talk about control structures, and in particular to talk about how we work over complex data structures. The main mechanism we use for control flow in Erlang is recursion. And what I want to do is remind you a bit about how lists are constructed and then talk about how we can use recursion to traverse lists and build up functions which are recursive over lists. So just to remind you, we can think of every list as being built up using the empty list and then adding an element at the head of a list. So for example, we can build the list 2, 3 by adding 2 to the list which has just 3 in it, and we can build the list 3 by adding 3 to the list that is empty. So given a list, it will either have this form or it will have this form. And if it has this form, this is itself a list. So that's the pattern that we'll see when we start writing functions that work over lists. We'll either have an empty list or we'll have a head, which is an element, and a tail, which is itself a list. Now, looking at the two examples that you see in this slide, what we have, we're trying to calculate the average of a list of numbers, excuse me, and we do that by calculating the sum of the list and dividing it by the length. So that's the top line, and what we then see are definitions of the function to sum the elements of a numeric list and a function to calculate the length, in fact, of any list. And what we'll do is just look through in more detail what's going on in that definition of sum. So what we have here is, I'll just echo this on the whiteboard. In the case that we have a non-empty list, what we say is take the head of the list and add it to the sum of the tail. And in the second case, we say the sum for an empty list is 0. You can think of this code, because it's a direct recursion, as actually describing what the sum is. If you're trying to say what the sum of a list is, well, you add all the numbers up. Given the list is constructed by adding h to this smaller list, what you're saying is to add all the numbers up, start with h, and then add up the remaining numbers. But let's see how that works. If you're not convinced, let's have a look at how this works in practice with the list 2, 3. So what is the sum of that list? Wait, that clause doesn't apply. It must be the first clause. So that will be 2 plus the sum of the list with just 3 in it. Now, what about that? We've got another case of the sum function being applied. In this case, the head of the list, h, is 3. Remember, we're pattern matching this against h cons t. H will match to 3, T will match to the empty list. So what we get is that this is 2 plus, what's that sum? Well, it's 3 plus the sum of the empty list. And then finally we get the result that the sum of the empty list is 0. So we can see that this is going to give us 2 plus 3 plus 0, which is what we expected. It's giving us the answer 5. So it's a nice description. You can write out the evaluation of functions written in this sort of way and convince yourself that that's the answer that you're getting. So that direct recursion, I'm going to contrast with what's called tail recursion a bit later on in this section. But the direct recursion is often the most straightforward way of writing this sort of function which traverses a list. Okay, so that gives us the sum, and I'm sure you can see that there's a pattern here. What we get for length, again the pattern is length of h cons on with tail is 1 plus length of the tail. In fact, we don't use h there, so what we can say is underscore and len of the empty list is again 0. And what you can see here is this pattern that you define the function over the head cons tail using the function on the tail. Exactly the same pattern there. And this thing is just defined directly. So this pattern of defining things mirrors the way that these functions are themselves created. So that gives us a recursive definition of sum and so on. If you're less familiar with this, and I know this can be a bit of a stumbling block when you first learn Erlang, we can look at this in a more imperative example, which I think can sometimes help persuade people that what's going on is not magic. It's simply the obvious way of iterating through a list. This has quite a lot in common with iterators for other languages. So what we see here is a function that runs through a list and printing out its every member. Let's assume it's a list of numbers. It's just printing out the numbers separated by a space. So again, we've got this pattern that you're either supplied with an empty list or you're supplied with a list whose first element is x and whose remainder is x's. This is another pattern people write for list recursions. In the case that you're presented with an empty list, you simply output a new line. That's what the twiddles n stands for there. In the case you've got a list whose first element is x, what happens in that in the body? Well, what's going on is you first of all evaluate the IO format, which prints the element, followed by a space, and then you print the rest of the elements. So what you're doing there is performing an action at the first element and then iterating to look at the rest. So rewriting this again, you can perhaps see even more clearly here. What we've got is this function print all. We do a case switch. Once you go into the function, if it's the same function, I've just rewritten it slightly. If the argument is the empty list, you output the new line. If not, so we've realized we've got a non-empty list, you output the element and then you call print all again. And that's just like a jump back to the start of the loop. So this is very much like a traditional control structure that you see in an imperative language. You have an out, you have a clause that exits the loop, and you have a general clause which re-enters the loop with some different arguments. And in fact, this is an example of what's called a tail recursive function. If you look at where the recursions happen, they come at the end of the bodies of the clauses. The only place that print all gets called is in the non-empty list case, and it's called as the last call. So that's what's called tail recursive, and tail recursive functions can be, I'm sure you know, can be implemented particularly efficiently because you don't need to create a stack frame for each call. You simply overwrite the existing stack frame. And in fact, it's like a loop which runs through with the variables of the loop being represented by the arguments of the function. We'll look at another example of that a bit later on. But I just wanted to show you that this pattern, just backing up here, what you're seeing is this pattern of a recursive function where you do one thing in the case of an empty list, another thing in the case where the list isn't empty, is very like a traditional iteration through a list in an imperative language, and that, as it's seen here in the example of sum, is the thing that allows you directly to compute the sum of a list. So that's what I hope will get you started on looking at recursion over lists. I think the way that you learn that is that we'll be supplying you with lots of exercises for you to try for yourself, different patterns of recursion. But what I'm going to do now is just talk through a number of examples, further examples, just to give you more, to give more weight to the idea of computing things by recursion. So here are 3 examples of patterns of recursion over lists. And some of these are things you see all the time. What the first function is doing is applying a particular transformation to every element of a list. What it's doing is it's doubling every member of a list. So we've got the same pattern. What if you apply it to an empty list? Well, the answer is you get an empty list back. In the case where the first element of the list is H and the rest of the list is the tail, you build a new output. Perhaps I'll just run through this on the board. In the case where you have the first element is H and the rest is T, well, what's the output going to look like? It will be itself a list, and its first element should correspond to H, so what we do is we double H. And then what do we do to the tail? Well, what we do is double the tail. So you can see, you can write that out by hand if you wish. Try that out and you'll see that what you get there is this, what we call a map function. A map is something that people do all the time with lists, and we'll see later on it fits in particularly well with filtering, which we'll see next, and comes into what are called list comprehensions, which are a very nice compact way of writing these things. So what we've done in the first function is we've doubled every element of a list. What I want to do now is write a function that will pull out the even elements of a list. And what I'm doing here is I'm going to use a guard. Let me just run through this again on the board. And what we have, we'll start off with the case where the list is non-empty. So we've got a head element and a tail element. But what we're going to have to do here is something rather different. We're not necessarily going to include H in the list. There'll be one case where we do and one case where we don't. So the case where we do is when it's even. So what we have to do is divide it by 2 and check whether or not that is gives us a 0 result. And if it does, what do we do? What does the output look like? Well, H is in the output, but what about the rest of the output when we apply to T? Well, what we're going to do is pull out all the even numbers from T. So here we see so what we've done is handle the case where HREM2 is 0, so H is even. Now what we have to do is handle the next case, and that's where H is odd. Now we could write explicitly HREM2 equals 1 there, but in fact we don't, because remember these things are evaluated sequentially, so we'll only ever hit this case when H is odd. So we know that H is odd when we get to here. So what we know is that it's not going to go into the output. So all we need to do is extract the even numbers that are in T. And in fact, because we don't mention it there, what we can do is replace it with a wildcard. And of course, we've got to finally do the last case, and that says that there are no even numbers in an empty list. So here we're using the guards to check the particular, whether that number is even or odd, whether it's even. And we are using the sequentiality here to write that more simply. I mean, you could, as an exercise, write this case using a guard so that you could reorder the clauses as you wish. So that's giving us what we call a filter operation. And map and filter are things that we do all the time when we're programming with lists. Now, let's have one final example. And what we're doing here is we're trying to check whether an element X belongs to a list H cons T. Well, there are going to be two ways that X could be a member of the list. It could be in there, could be equal to H, or it could be a member of T. So what we do, and what you can see in the definition there on the slide, is in the first case we can use pattern matching to say, well, if the thing we're looking for is equal to the thing at the beginning of the list, the answer is true. Otherwise, we're going to have to check whether that thing is a member of the tail of the list. And then finally, we return the result false, whatever we're looking for in an empty list, because the empty list has no members. But the first two clauses correspond to the case where, first of all, the number we're looking for is equal to, the element we're looking for is equal to the head of the list. And the second case, what we're doing is we're returning the member itself. Perhaps what you'd like to do as an exercise is just have a two-clause definition, where the first clause looks like this. Sorry, looks like this. And the second clause is as we've seen. And for you to think about how to define it like that, using an equality and a recursive call. So that's an interesting exercise to do. Just beginning to get your head around the way these recursions work. Now, we've talked quite a lot about, and all these examples here are pretty much direct recursions. Where in fact member happens to be tail recursive. But what we've got there is a description of, I think all of these are self-describing, if you like. And what I want to do, and examples of direct recursion, what I want to do to finish this section is to talk a bit more about tail recursion. So let's go back to the example of calculating the sum of a list. And we'll look at the slide in a second, but the sum gives us a slightly simpler example. And what we've said is the direct definition looks rather like this. So directly we have the sum of the list, whose first element is H, whose tail is T, is got by adding H to the sum of the tail. Now what we can do instead is think about using one of the arguments of a function to store the result of making the addition so far. And let's try and think about how we might do that. What we're going to do is write a new function. Let's call it sum ac. And what we're going to do with this is we're going to have the list in the first argument, and we're going to have the sum in the second. And when we've exhausted the whole list, what we do is just output the sum. But suppose what we're doing instead is we've got the list which has a head H and a tail T, and we've got the sum so far is S, what's the result going to be for this? Well, what we want to do is take off h and add it to s, and then restart with the tail there. So this will look like in this form. I'm sorry. Let's write it down here. Sum ac. Now we've just got the tail left, but what we've got now is we've got the head added to what we had so far in that variable there. Now the question is, how do you start this off? And the answer is that you can calculate the sum of a list by starting off the sum accumulator with the list, and the sum so far is 0. So what we've done now is we're using this second position here really just like a variable. We start off initializing the variable to 0. When we get to the end of the list, we return what's the result of the variable. But what we do here is we go from the list to its tail, but when we do that, we add the head to the sum so far. And let's just look at an example of how that works out. And this does look very much like imperative programming. I think we looked before at the example of 2 and 3. It should look more like a 2. And what that becomes is sum ac 2, 3 followed by 0. Now, which of these clauses applies? What we have, first of all, let's just rub that out so it's clear what we're doing here. We take the first element off the head, off the list, and add it to the sum. So this becomes sum ac list, which is 3 in, and we add 2 to there. Again, we take the first element off there, and we get list with nothing in, and the sum so far now is 5. And then finally this clause says, well, we've reached the end, so the answer is 5. Now what's nice about this is that what you've got here is a tail recursive function. It can be, the only thing you do in the body there is call the function again. So it can be implemented in some situations more efficiently. So tail recursion is particularly in when we start looking at concurrent programming, we'll be looking a lot at tail recursive functions. But in this particular case, we're getting something more efficient as a definition. But what I would say is that we've got something which is rather less straightforward to understand. If you compare this to what we had before, where directly we said what the sum of this list was, and that sum of the empty list is 0. So directly that says what the sum is. What we have to understand here when we're reading this definition is we have to understand how these two arguments change as the function is called. So we have to understand that we start off with 0 there, and we gradually accumulate the result in that variable as we're iterating through the list there. So it's a different pattern. It's one that you can easily get used to using, but is perhaps less direct than that. So just to underline what's going on, we use these positions, if you like, as variables. This extra argument here acts like a variable to store the sum so far. And what you see in the slide is a rather supercharged version of this, where what we do is as we run along the list, we simultaneously calculate the length in the second variable and the sum in the third. So what we're doing is we've got two accumulator variables which separately calculate length and sum, and then we get the average, as you see in the final clause. When we've got to the end of the list, we divide the sum by the length. Just worth being aware that you would get a runtime error if you applied this to an empty list, so perhaps we needed a separate clause for that, and that would be a good exercise if you want to try that. Okay, well that's come to the end of what I wanted to talk about control structures in Erlang. We've talked about alternatives using case and if, and we've talked about loops, and iteration through data structures using recursion. And that really that's a crucial part of the way that the machinery of Erlang for doing day-to-day programming tasks. And I think the way to get comfortable with that is to try a whole lot of examples.